welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about elements, compounds, and mixtures. Our aim for today is, how can we classify matter as elements, compounds, homogeneous or heterogeneous mixtures? Let's draw a diagram to better categorize the four components of matter. So, everything is made up of matter. But we can break that down into two subcategories. The first one is pure substances, and the other is mixtures. Substances, or pure substances, sometimes the Regents calls them just substances, mean the same thing, substances or pure substances, also breaks down into two categories. We have elements and compounds. Mixtures also break up into two categories. There is homogeneous or homogeneous, and heterogeneous. An element, a phrase you'll frequently see on the Regents, cannot be broken down by chemical means. On the periodic table of elements, we have 118 different elements, and they're represented by either a capital letter or a capital letter and a lowercase letter. For example, you can have carbon, which is C, sodium, which is Na, a gas like neon, which is Ne. And we'll have some elements that are called diatomic elements or diatomic molecules that can only exist in nature in pairs. We'll talk about those later on. Oxygen is one example. So the oxygen you breathe is not just O, it's O2. A compound are two or more elements chemically combined in fixed proportion. So if you see two or more capital letters, that is going to be a compound. So for example, we could take carbon and oxygen, put them together, and get carbon dioxide, which is capital C, capital O, and there's two oxygens in CO2. You could also have water, which is H2O. Capital H, capital O, there's two H's, but since there are two capital letters, two different elements, that's what makes it a compound. You can also have our old buddy glucose, which hopefully you remember from living environment. Glucose is C6H12O6. Or even a simpler one, sodium chloride, table salt, Na, capital N, lowercase a, capital C, lowercase l, NaCl for sodium chloride. Homogeneous mixtures they have particles in there. It's a mixture, and the particles are distributed uniformly. So an example of a homogeneous mixture or homogeneous mixture would be something that you know is a mixture of compounds, but you can't see the individual components. So if you ever made iced tea from the powder, if you stir it well enough, you shouldn't see the individual components. It should look like one brown mixture. Or if you were to, just even simpler, take salt and mix it with water. Salt water, you have the compound sodium chloride, NaCl, you have the compound water, and you mix them together, and if you were to look at it, it should look like one uniform mixture. The opposite would be heterogeneous mixture. Particles are not distributed uniformly, or they're non-uniform. So if you look at a heterogeneous mixture, you would be able to see the individual components. So for example, if you had a Caesar salad, you could pick out the individual components. You have the lettuce, you have the croutons, you have the dressing. Maybe if it's a chicken salad, you have the grilled chicken on top. A pile of garbage, right? If you go to the garbage, you can pick out the paper plate, the paper cup, the fork, the knife, the crumpled up napkin, the piece of gum. They're all different components. Or a pepperoni pizza. If you have a pepperoni pizza, you have the dough, the sauce, the cheese, the pepperoni. You can individually pull off those components and separate them. They're so big, they're big enough you can see them, and obviously it's non-uniform. You look at a pepperoni pizza, you don't just see one thing, you see the individual components. Once again, the cheese, the sauce, the dough, etc. Another example, one more example would be chicken noodle soup. You have the noodles, the chicken, the broth. You put any vegetables, maybe some celery, put some cheese on there, some Parmesan cheese. Those are all different components. That is a heterogeneous mixture. Here we have two different elements, iron and sulfur. Iron has the symbol Fe, capital F, lowercase e. It can be found on the periodic table, and it is element number 26. Sulfur, represented by the capital S, is element number 16 on the periodic table. Now, if I take this magnet and I put it over the sulfur, nothing happens. Sulfur is non-magnetic. However, iron, if I place the magnet over the iron, it picks up the iron because the iron is magnetic. I'll put that back in. Now, if we were to mix these two together in this third watch glass, you could still see the yellow sulfur and the black iron as two separate components. So we would say that these are non-uniform. So what we have here is iron plus sulfur. We have a heterogeneous mixture. I can see the two components, the yellow sulfur and the black iron, and I could also separate the iron using the magnet. These two elements here in the heterogeneous mixture retain their original properties. Sulfur was non-magnetic, and the iron is magnetic. Here we have a few different compounds. The first compound, this purpley crystal, is cobalt chloride, represented by capital C, lowercase o for cobalt, and capital C, lowercase l for chloride. As you can see, it has a 1:2 ratio, a 1 cobalt to 2 chlorine ratio. Two or more elements, chemically combined in fixed proportion, 1:2, that is a compound. Calcium hydroxide, CaOH2, is another compound. You have calcium, oxygen, and hydrogen. Here we have 3 different elements. Now that 2 gets distributed to both the O and the H, so we have a 1:2 ratio. Once again, 2 or more elements, in this case 3 elements, chemically combined in fixed proportion. That is another compound. And of course, as we talked about, we have water, 2 beakers of water, which is H2O, and water is a compound. It's a 2 hydrogen to 1 oxygen ratio, and that is another compound. From here, we could mix the cobalt chloride into the water, and we can stir. As you can see, it is dissolving and making somewhat of a purple mixture. We could also take the calcium hydroxide and put it in water. And we get a white liquidy mixture. What we have now are 2 homogeneous mixtures. On the left, we have cobalt chloride dissolved in water, and it looks uniform. There are no particles on the bottom. So we have one mixture that looks the same throughout. So cobalt chloride dissolved in water, or CoCl2 aqueous, is a homogeneous mixture. Remember, anytime you see the 2 letters AQ after the symbol, then you have a homogeneous mixture. Similarly, we have calcium hydroxide dissolved in water, and you can see this white liquid looks the same throughout, a homogeneous mixture. And once again, you have CaOH2, AQ. The AQ, aqueous, means that it is a homogeneous mixture. From here, we can take these 2 mixtures and mix them together. And stir. Remember, the cobalt chloride was a purplish color. The calcium hydroxide was a whitish color. And now we're left with, after mixing them together and stirring, is this blue solution. What we have made when we mix these 2 solutions together is calcium chloride, aqueous, and cobalt hydroxide, solid. Together, this is a heterogeneous mixture. Let's take a closer look. Inside of the beaker, you can see this light blue liquid on the top. That is the aqueous calcium chloride. So here on the top, we have a homogeneous mixture. And on the bottom, this dark blue solid, the cobalt hydroxide, that is a heterogeneous mixture. You can see all of the particles floating here at the bottom. So once again, on the top, the calcium chloride aqueous, that's your homogeneous mixture. Remember, AQ, aqueous, is going to give you a homogeneous mixture. And down here, the cobalt hydroxide solid, that is a heterogeneous mixture. Together, the calcium chloride and the cobalt hydroxide, the whole beaker in total is going to be a heterogeneous mixture. Now, matter can be broken down into two subcategories: pure substances and mixtures. We're going to start off with pure substances. Pure substances can be broken down even further into elements and compounds. An element is a substance that cannot be broken down into simpler substances by physical or chemical means. There are 118 elements on the periodic table. Now, an element is represented by either one or two letters. If it's an element, the first letter will always be capitalized. If there is a second letter, the second letter will be lowercase. Now, there are elements that just are one capital letter. For example, carbon, capital C. Potassium, capital K. Or tungsten, which is represented by capital W. There are also elements that are represented by two letters, one capital, one lowercase. We have some here. We have calcium, Ca, capital C, lowercase a. Still only one capital letter. Sodium, capital N, lowercase a. Iron, capital F, lowercase e. In each instance, one capital and one lowercase letter, but only one capital letter. And finally, we have diatomic elements, or also known as diatomic molecules. These elements can only exist in nature in pairs, diatomic, two atoms. So for example, fluorine wouldn't just be F, it would be F2. And the nitrogen in the air wouldn't just be N, it would be N2. The oxygen that you breathe would not just be O, it would be O2. We'll talk a little bit more about this later. And the other type of pure substances are compounds. Compounds are matter that is composed of two or more different elements chemically combined in fixed proportion. And they're represented by multiple capital letters. For example, we have H2O, water. We have two capital letters, H and O, and they're in fixed proportion. Every water molecule in the universe will always be two hydrogen atoms and one oxygen atom. Fixed proportion, a 2-to-1 ratio. We have also down here carbon dioxide, CO2. Carbon and oxygen, we have two capital letters, capital C, capital O. We have two oxygens, and that's the ratio. We have a 1-to-2 ratio in this case. For every one carbon, there are two oxygens. Here, like we said, it's a 2-to-1 ratio. We have more complex compounds, like table sugar. Sucrose is C12H22O11. So we have three different capital letters, capital C, capital H, capital O, carbon, hydrogen, oxygen, and the ratio is a 12-to-22-to-11 ratio. Every sugar molecule, every sucrose molecule will be the exact same ratio, 12 carbons to 22 hydrogens to 11 oxygens. You could also have compounds with one capital letter, one lowercase letter, another capital letter, another lowercase letter, such as sodium chloride, which is table salt, capital N, lowercase a for the sodium, capital C, lowercase l for the chlorine. As promised from before, we have to discuss diatomic molecules. Now the word diatomic has a prefix di, di, which means two. And atomic, of course, refers to atoms. So diatomic means two atoms in a molecule. Diatomic molecules are molecules composed of two atoms of the same element. Now there are 7 diatomic molecules. Br, which stands for bromine, represented by Br2. I for iodine, represented by I2. N for nitrogen, represented by N2. Cl for chlorine, represented by Cl2. H for hydrogen, represented by H2. O for oxygen, represented by O2. And finally, fluorine, represented by F2. Now the bad news is you're going to have to memorize that there are 7 different diatomic molecules, and you have to memorize which ones are diatomic molecules. However, the good news is there is a mnemonic device to help you remember these 7 diatomic molecules, and that is Brinkelhoff. B-R-I-N-C-L, Brinkel, Hoff, H-O-F. Br for bromine, I for iodine, N for nitrogen, Cl for chlorine, H for hydrogen, O for oxygen, and F for fluorine. Brinkelhoff. Those are your 7 diatomic molecules. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Brinkelhoff. And then we have mixtures. Mixtures can also be broken down into 2 categories: homogeneous mixtures, or homogeneous mixtures, and heterogeneous mixtures. A homogeneous mixture is a mixture that has a uniform composition, keyword uniform, composition throughout, and always has a single phase. So it always looks the same throughout. Homogeneous, the prefix homo means same, so it's not the same throughout. Although the proportions will vary. And it can be separated by a process known as distillation. We'll talk about this more when we talk about the different ways to separate mixtures. Now, for example, NaCl, which is a compound, and then we have these 2 letters AQ after it. That means, so NaCl is sodium chloride, and this AQ means dissolved in water. NaCl is a compound, sodium chloride, and this AQ means dissolved in water, which makes it a mixture. Now think about taking salt and water, dumping the salt in the water, the table salt into the water, and stirring it thoroughly. If you look at that salt water, it should look uniform. You shouldn't be able to distinguish the different NaCl particles in the salt water. It should all look the same. Another example of a homogeneous mixture, this time in the solid form, is bronze. You might see something that looks like this. Now, bronze is made of copper, Cu, and tin, Sn. If you see something like this, Cu plus Sn, that is going to be a mixture of some sort. Now, if you look at bronze, like the 3rd place metal, you have gold first, silver second, and bronze third. If you look at bronze, it's going to look uniform. You can't see the different parts of the copper and the different parts of the tin. They're heated up, mixed together, and then they're molded into a metal in this case. Now, bronze is a mixture because it contains somewhere between 90 and 95% copper. You could have 90% copper and 10% tin, that would be bronze. Or you could have 95% copper and 5% tin, that would also be bronze. A homogeneous mixture has uniform composition, but the proportions may vary. Anywhere between 90 and 95% copper for bronze, and anywhere between 5 and 10% for tin. Same thing with salt water. You can take a glass of water, and you can put 1 teaspoon of water and stir it. You can put 2 teaspoons, 3 teaspoons. As long as it all dissolves, that is still salt water. Might be a little bit salty or very salty. But in either case, if you can't see the individual grains of salt, it's a homogeneous mixture, uniform throughout. And finally, we have heterogeneous mixtures. A heterogeneous mixture is a mixture that does not have a uniform composition. So we could say it is non-uniform. And in which the individual substances remain distinct. So let's look at the word heterogeneous. The prefix hetero means different. And in a heterogeneous mixture, you can see all of the individual components. A great example would be chicken noodle soup. If you had a bowl of chicken noodle soup, you can see all of the distinct components of that chicken noodle soup. You see the chicken, you see the noodles, and you see the broth. Maybe you have some carrots in there, some celery, some cheese. And you can actually take your spoon and separate the different components of that chicken noodle soup. You can pull out the chicken, then you can pull out the noodles, the celery, the carrots, and you're left with the broth in the bowl. Another example would be a pepperoni pizza. A pepperoni pizza, you see the individual components of the sauce, the cheese, the dough, the pepperonis on top. You can pick off all of those different substances and separate them by hand in this case as well if you would like. So heterogeneous, non-uniform, they look different. You see the different components, the chicken, the noodle, the soup, etc. The sauce, the cheese, the dough, the pepperoni, etc. That's a heterogeneous mixture. Let's do some examples together. Here we have a data table with a bunch of different substances. And for each substance, we must determine whether it's an element, a compound, a homogeneous mixture, or a heterogeneous mixture. For the first one, we have tungsten. Now, tungsten is one of the elements on the periodic table of elements. It's represented by the capital W. So very simply, capital W, one capital letter, that's an element. Tungsten's an element. For the second one, carbon dioxide, represented by CO2, we have two different elements, carbon and oxygen. Chemically combined, they're together in a fixed proportion. It's a 1 carbon to 2 oxygen ratio. So 2 or more different elements chemically combined in fixed proportion, that's the definition of a compound. So CO2, or carbon dioxide, is a compound. For the third one, we have skim milk. Now, if I have skim milk, I'm picturing a glass filled with this white liquid. Now, there's no element known as skim milk, and you can't put a couple elements together and make a compound and have skim milk. Therefore, skim milk must be a mixture. It must be on the right side of the data table, either a homogeneous or a heterogeneous mixture. Now, we have to think of the words homogeneous and heterogeneous. Prefix homo, meaning the same, means that this mixture will be uniform. It will look the same throughout. Whereas a heterogeneous, hetero meaning different, will be non-uniform. It will look different throughout. So back to skim milk, if I have that glass of that white liquid, I'm looking at it, it looks the same, it looks uniform. There's no components that I could see with my naked eye, just that one white liquid. So since it looks the same, it looks uniform, it is a homogeneous mixture. For the fourth one, we have Greek salad. If we had a bowl of Greek salad in front of us, you would see lettuce, tomatoes, cucumbers, black olives, chickpeas, feta cheese, Greek dressing, maybe some other things. Obviously, there's no element that's a Greek salad, and there's no combination of elements to make a compound that would be Greek salad. So once again, we're on the right side, either homogeneous or heterogeneous mixture. Now, since you look at that Greek salad and you see the different components, you actually pick out the lettuce, the tomato, the cucumbers, the olives, the feta cheese, so on and so forth. Since they're all different components, you see the different components, that gives us a heterogeneous mixture. For the next one, we have hydrochloric acid, which is HClAQ. Now, HCl, I see two capital letters, represents two elements, hydrogen and chlorine. So if we didn't have that AQ, that would be a compound, two or more elements chemically combined in fixed proportion. But we have these two letters here at the end, AQ, which stands for aqueous. And that means dissolved in water. If we just had HCl, hydrogen chloride, that would be a gas. But hydrochloric acids, when you take that HCl gas and dissolve it in water, it makes it a mixture. We have a mixture of hydrogen chloride and water. Anytime you see that AQ at the end, it's going to be a homogeneous mixture. For the next one, we have brass. Brass is very similar to bronze that we talked about before. Brass is made up of copper and zinc, two different elements, but they're not chemically combined. And that is given away by this plus sign in the middle. Anytime you see a plus sign in the middle of your symbols, that is going to be a mixture. It's copper plus zinc. How do you make brass? You take copper, you heat it up, take zinc, heat it up until it's melting point, until it's liquefied. You mix them together, you cool them down in a mold. So it is a mixture of copper and zinc. So once again, on the right side of the data table. Now think about brass. If you had a brass lamp, or a brass doorknob, or anything made of brass, it's going to look uniform, it's going to look the same. It's going to be that brownish, shiny metal. So if it looks the same throughout, if it looks uniform, brass is a homogeneous mixture. Cu plus Zn is a homogeneous mixture. And it has varying proportions. Two different pieces of brass could have different amounts of copper and different amounts of zinc. The proportions vary. For the next one, glucose, C6H12O6. I see three capital letters, therefore it's three different elements. And it's chemically combined in a 6:12:6 ratio, or to simplify that, a 1:2:1 ratio. So glucose, two or more different elements chemically combined in fixed proportion, is a compound. Methane is CH4. Once again, we have two different elements. They're chemically combined. There's no plus sign in between these two elements. In a fixed proportion, a 1 carbon to 4 hydrogen ratio. So once again, two or more different elements, chemically combined in fixed proportion, that is going to be a compound. Helium. Capital H, lowercase e. One capital letter. Helium can be found on the periodic table. Yes, that's the same helium you put in a balloon to make it float in the air. Helium is element 2 on the periodic table, one capital letter, therefore helium is an element. A chocolate chip cookie. There's no element and there's no compound that makes chocolate chip cookies. It's a mixture of elements and compounds. So once again, we're on the right side of the data table. If you think of a chocolate chip cookie, you have the cookie part, and you can actually pick out the chocolate chips. It looks non-uniform. You can see the different parts of the chocolate chip cookie. Therefore, a chocolate chip cookie is a heterogeneous mixture. And finally, we have blood. If you've ever donated blood, or you had to go to the doctor and they took blood to analyze it, they take this red liquid from your arteries and veins. So that red liquid, there's no element that's blood, there's no compound that's blood. It's a mixture of elements and compounds. And if you look at that tube With your blood in it, it looks red and it looks the same throughout. It looks uniform. So blood is considered a homogeneous mixture. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned about matter. Matter is anything that has mass and takes up space. We learned that matter can be broken up into two subcategories, pure substances and mixtures. Pure substances are either elements or compounds. Mixtures can either be homogeneous or heterogeneous. Thank you again for joining us. I hope you learned something today. Please join us again soon.